scientists have stumbled upon a rather perplexing occurrence concerning the Higgs boson, which casts doubt on our current understanding of this fundamental particle. What they've witnessed is an unexpected decay of this exotic particle, far exceeding the boundaries set by the standard model of physics, the very framework that has served as our guide thus far. These unforeseen revelations are challenging the very fabric of our predictions, hinting at the tantalizing prospect of entirely new physics awaiting discovery. But let's backtrack a bit and delve into what exactly the Higgs boson is and how it fits into the grand scheme of things, using a down-to-earth analogy we can all relate to. Imagine the universe as a colossal swimming pool, not filled with water, but with an invisible substance known as the Higgs field. Now picture different types of swimmers navigating through this pool. First up, we have the pros. Those streamlined, efficient swimmers who glide through the water effortlessly, barely making a splash. They're akin to particles like photons, zipping along without a care, unaffected by the Higgs field, and thus, they remain massless. Then there are the casual swimmers, perhaps not as graceful, causing a bit of a commotion with their splashes and waves as they navigate through the water. These are like electrons and quarks, interacting with the Higgs field, which is why they possess mass. Now toss in an inflatable beach ball into the mix. It's not exactly nimble on its own. It takes some effort to get it moving. This beach ball represents the heavier particles like the W and Z bosons, which heavily interact with the Higgs field, hence packing a considerable mass. And let's not forget about the ripples, those waves that dance across the pool's surface whenever the swimmers make a move. That's where the Higgs boson comes into play. When a particle engages with the Higgs field, it stirs up a disturbance, much like those ripples, a quantum excitement, if you will. When we caught a glimpse of the Higgs boson at the Large Hadron Collider, it was akin to spotting those telltale ripples, affirming the presence of particles engaging with the Higgs field. However, here lies the conundrum. The Higgs boson doesn't stick around for long. Once it's whipped up in particle collisions, the famed particle barely sticks around. Less than a trillionth of a billionth of a second, to be precise. That's 1.6 times 10 at minus 22 seconds, making it a real headache to study. It's like blink, and you'll miss it. So, how do physicists even begin to unravel the mysteries of such fleeting particles? Well, they turn to its decay modes. Picture this. The particle can break down in various ways, or modes, depending on the conditions. And the recent buzz surrounding the Higgs boson involves its transformation into another batch of particles. Let's circle back to our swimming pool analogy. Imagine our pool's wave, or the Higgs boson, getting too rowdy to handle. What's its next move? It needs to chill out, right? And how does it do that? By breaking down into smaller ripples or waves. Now picture these smaller waves as other particles. Depending on the initial size and energy of our big wave, or the Higgs boson, it could split into a duo of smaller identical waves. Think a pair of W bosons, Z bosons, or tau leptons. It might even cook up a mix of waves and tiny bubbles, like a pair of leptons and photons. Now here's where it gets tricky. The Higgs boson's decay into two photons isn't a simple flick of the switch scenario. It involves a complex mechanism called a loop, where virtual particles pop in and out of existence. These virtual particles might include hypothetical ones that we've yet to spot, making their direct detection a no-go. Interestingly, this process isn't exclusive to photon decay. It also plays a role in the Higgs boson's transformation into a photon and a Z boson, which is what's got everyone buzzing. The Z boson is the heavyweight champ of the standard model, an elementary particle that, along with the W boson, carries the weak nuclear force. At the Large Hadron Collider, researchers rolled up their sleeves to dig into this rare decay process. According to the standard model's predictions, only a tiny fraction, roughly 0.15%, of Higgs bosons should decay into a Z boson and a photon. However, the experimental data collected from proton-proton collisions at the ATLAS and CMS detectors between 2015 and 2018 tells a different tale. Shockingly, the data reveals that this decay is happening in roughly 6.6% of cases, a major deviation from what was expected. Both experiments pinpoint the Z boson by tracking its subsequent decay into pairs of electrons or muons, with the frequency of these decays hovering around 6.6%. At the Large Hadron Collider, The ATLAS and CMS experiments pulled out all the stops, implementing savvy strategies to amp up sensitivity in detecting the Higgs boson's decay into a Z boson and a photon. They honed in on the most common modes of Higgs boson production and leveraged cutting-edge machine learning techniques to effectively sift through signal and background events. The result? The first tantalizing evidence of this decay process. Now, here's the kicker. The statistical significance of these observations clocks in at 3.4 standard deviations, just shy of the conventional threshold of 5 standard deviations needed to seal the deal. This means there's a slim chance these findings could be a fluke. Still, the measured signal rate strays from the standard model's predictions by 1.9 standard deviations, making it a noteworthy result that demands attention. For eons, the Higgs boson has reigned supreme as a linchpin of the standard model of particle physics. But these fresh insights hint that it might not be the whole story. It could be nudging us toward new avenues or tweaks to the existing model. Nevertheless, this study serves as a rigorous litmus test for the standard model and its forecasts. As we gear up for the ongoing third run of the LHC and the future high-luminosity LHC, scientists are brimming with anticipation for even more precise measurements and the exploration of even rarer Higgs boson decays. These future endeavors hold the promise of delving deeper into the fundamental essence of particles and their interactions. Enjoying this dive into particle physics? Don't forget to check out our video where we tackle the mind-bending challenges of venturing beyond our solar system. And if you are curious to see more of any of the subjects from these videos, leave it here in the comments and take the opportunity to like the video and subscribe to the channel for more videos like this.